We had derived from the non-dimensional equation.
Hey, first dimensional form. Before non-dimensionalization, we linearized, right?
Okay.
We linearized the system.
Minus alpha t dash
Huh.
g vector
Mm.
plus nu del to u u dash vector.
Right. Okay. And then we obviously have del dot u prime equals 0. And then we have del t prime over del t. And then here we had a
Minus v dash
minus v prime
minus v prime
delta t
delta
over a capital H, right?
yes
Equals kappa del square t prime. Okay. These were our linearized equations in the dimensional form. And then to non-dimensionalize these, what did we do? How did we non-dimensionalize? So we can take, let's say, x, y, and z, and then we have a gravity. So the velocity scale that we chose, or rather the velocity perturbation scale that we chose, was based on the thermal diffusivity, right? We had kappa over capital H. And then the pressure scale was basically rho naught kappa over H square. So if you call this U naught, then it makes writing easier, right? And then the temperature perturbation scale was delta T. So delta T is basically TH minus TC. Okay, that's what your delta T is. And then the length scale was capital H, and the time scale you can get from basically L by U. So you'll get H square over kappa. So this is your thermal diffusive time scale. Okay, this is your thermal diffusive time scale. And then from here, what we saw is when you non-dimensionalize the equation. So let us write the non-dimensionalized equations. So we will have this equals, so the pressure term and the unsteady term had the same coefficients in front of them, del star p prime star over rho naught. And here what do you get? Minus alpha, what was that which we called Rayleigh's number? So this will go away, right?
alpha delta t
Hmm.
h cube
H cube
by nu
into kappa.
t dash t prime
Yeah.
g sorry t prime star g
G vector, right? And then I can write a G vector by writing it as G star and then multiplying it with the, okay. So G star is nothing but by G. So it's simply minus J cap. Okay. Non-dimensionalized G star is this. And then we had nu by kappa del star square u prime star, right? We had a Prandtl number, right? Or 1 by Prandtl number. What did we have?
that is where I have a doubt. You had introduced the Prandtl number into this, and we're not sure how you introduced it.
No, because I had multiplied it with kappa by nu to get this form, and then I had again divided by kappa by nu to get this.
So kappa when you use the Prandtl number.
Nu by kappa is the Prandtl number.
So there was
Actually, it's not nu by kappa.
nu by
Yeah, nu by alpha. Alpha, let's not talk. So there was some. Was there? Let's see. So what do we get here? Nu over h square del star square, and then a. So yeah, this shouldn't have been kappa actually. This should have been this. It's okay. if the students are not here, I don't really. So this shouldn't have been kappa actually. This should have been. So if this guy is kappa, actually yeah, this is fine. No, it's fine. So we are calling it as kappa in our problem, which is usually denoted by alpha. Okay, because I already have an alpha here. I already have an alpha for the thermal expansion coefficient. So this kappa is actually thermal conduction coefficient by rho naught Cp. Okay, so nu by kappa, this kappa is Prandtl number. Okay, and then here this is your Rayleigh's number. Okay, this is your Rayleigh number. So we'll get del u. So if we write these equations for the for each of the components, and we'll drop the stars now. We'll drop the stars. So del u prime by del t equals minus grad of p prime minus the Rayleigh number times, actually Rayleigh number term will not appear in the x momentum equation. Okay, so you have simply minus del p prime over del x plus Prandtl number del square of u prime. Okay, and then in the y momentum equation we will have minus the Rayleigh number times a t prime, and then g star is minus j cap only. There was a minus here or plus? Minus here. So this should be, this is okay. So plus RA t prime plus a Prandtl number of del square of v prime.
Should be Rayleigh into Prandtl for T prime.
Yeah, you're right. Because Rayleigh number is alpha delta t h cube g over nu square. That's how we are defining Rayleigh number. Or no, hold on. Let me see. But then this should be fine, right? Or actually I'm missing something here. Actually, this is the correct state. This is what the equation was. So then when you again multiply with nu by k, then you will get a kappa square, and this is your Rayleigh number. Okay, and then if you have to make it kappa square, then we write Rayleigh into Prandtl, which is alpha delta t h cube g over kappa square, which is what will appear here once we multiply with nu by kappa. So this is RA PR, and then we have the Z momentum equation, which is very straightforward, nothing going on except for, okay, these are our momentum equations, dimensionless momentum equations. So you see the effect of this temperature difference and that leading to some movement of the flow, let's say, which is something you would expect, that you are heating the fluid from bottom, so it should go up. Okay, if you're heating the fluid from the bottom, it will go up, and then del w prime over del t is this, and then the coupling of temperature and momentum is only in the y momentum equation. So at the linear approximation, within the linear approximation, the temperature difference only starts affecting y direction velocity. It's after that you will start seeing, since you guys probably know about Rayleigh-Bernard convection, it's the nonlinear stage of this linear instability. Okay, you keep a fluid in a pan, you start heating it from the bottom, it will start this instability, it will form those natural convection currents, and after some time you will start to see the pattern at the top, which is the Rayleigh-Bernard patterns, Rayleigh-Bernard cells that you know. That's the nonlinear regime of this Rayleigh-Taylor instability. Okay, So this is our momentum equation. Continuity is very straightforward. And we have seen how to derive this. And then we have the temperature equation. We have the temperature equation, which is, so when we non-dimensionalize this, what did we get? When we non-dimensionalize this, minus v prime, right? Because we have this. So here we will have a delta t over time, which is h square by k. So h square k. And then we have a v prime delta t over h, and v prime will introduce. So when I make this quantity a star, I will introduce another k by h. So this will also be this. And then here as well, when I introduce these quantities as stars, I will have a k delta t over h square. So same coefficient appearing in front of all terms. So then we get a del t prime over del t minus v prime equals del square t prime. All dimensionless. Okay, these are all dimensionless. So now we have our linearized system of equations. Okay, we have our linearized system of equations. We have our linearized PDEs. Okay, there is one more step before we can start analyzing the instability of this, and that step is the, what is that step? Normal mode assumption. So the normal modes for us will be, let's say, complex exponentials in which direction? So let us say I decide to write one phi prime, which is basically a combination of all of my variables, u prime, v prime, w prime, t prime. Might as well throw p prime in this. Okay, this is going to be what? P prime is going to be p hat function of omega. What are the two homogeneous directions? X and z. So k x, k z, and y, e to the power I omega I kxx plus kyy minus omega t. This is the very important starting point. Okay, kzz. Sorry, I always make this mistake. This is a very important starting point of your stability analysis. Okay, ask any questions if you have here, because once we move here, we are really converting a system of linear PDEs to linear ODEs. Okay, so it is very important that you understand how this is written. This is nothing but a Fourier expansion in x, z, and time. Okay, nothing but Fourier expansion. So now substituting this for phi prime, we know that all of the partial derivatives in time are going to be minus I omega times. So we are going to get minus I omega times u hat equals minus I kx times p hat plus Prandtl number times d2 by dy square minus kx square plus kz square times a u hat. And then we have a minus I omega v hat equals d minus dp hat over dy plus Rayleigh into Prandtl into t hat plus Prandtl into d2 over dy square t v hat. I k z p hat okay. And then all of these u hat, v hat, w hat are related through the continuity equation. So we have I kx u hat plus I kz w hat plus dv hat over dy equals 0. And then we have the temperature equation minus I omega t hat minus v hat equals d2 by dy square minus kx square plus ky square T hat.
So what is the first one we LHS of the third equation? Iota omega.
W hat. The
No,
Z
the first term on the RHS.
RHS minus I K Z P hat, no? You have del P prime by del Z. So you just replace the partial derivative in Z with this. Okay. Okay. So we have a system which is not very different from what we have looked so far. Okay. The standard technique in these systems, whenever you are looking at incompressible fluid dynamic systems and looking at their stability, linearizing the governing equations, and you have viscosity. Even if you don't have viscosity, there is a way to do this. Okay. But when you have viscosity, then the standard trick is, as we have done for our Sommerfeld equation, and that is you just take a Laplacian of your y momentum equation. Okay. Now you can take a Laplacian in here or you can take a Laplacian in here, it does not matter. Okay. And the reason why we do that is because we are looking for an equation in one variable. Okay. We have a system of equations, you can solve this. Okay. This is also this is also an eigenvalue problem. Okay. You can write this as, so you have minus of I omega u hat v hat w hat t hat. Okay. You can write this as a system times a u hat v hat w hat t hat. Okay. You will see that there is a pressure, there is an annoying pressure that exists here, and you can actually eliminate that pressure by doing what? We can eliminate the pressure by adding these equations and multiplying them with these. Basically, we can eliminate the pressure by taking a divergence of our momentum equation. Okay, del by del x of this plus del y of this plus del by del z of this. The reason why we do that is all terms are linearized in velocity, pressure, wherever all terms are linearized. So the moment you take any divergence, all the velocity terms are going to go away. Okay, so these terms will go away when you take the divergence and add. These will convert into a Laplacian of pressure, and this will go away, this will go away, this will go away, and you will be left with a y direction derivative of temperature profile. Okay. So you can replace pressure from that. So let us try to do that, and then we can write the system in this form, in the matrix form, and this is your differential eigenvalue problem. Okay. To form this, we have to eliminate pressure, and what we see is minus del square of p prime from here plus RA into PR into del T prime over del Y equals 0, or d square minus so d2 by dy square minus kx square plus kz square pressure equals RA into PR into dt hat over dy. Okay. So you have a system of equations and you can eliminate pressure using this. Okay. It's a bit cumbersome to do that, but you can numerically solve this system as well. What will be the boundary conditions? Let's talk about boundary conditions for a minute. What will be the boundary conditions? So we have plates on both the ends. Okay, these are hard walls. So these are hard walls. So we have u hat equals 0 at y equals 0 comma 1. We are looking at dimensionless coordinates. Okay, so y will be 0 and 1. We have v hat equals 0 at y equal to 0 comma 1, and we have w hat equals 0 y equal to 0 comma 1. Okay, we have these conditions. This is your hard wall condition, and these two are no slip conditions. Now you see there is another variable in this problem, and that is temperature. So physically you can have a wall, but there is still a degree of freedom in a way in how this wall is being maintained at a temperature, or is there a constant heat flux boundary condition. So from temperature perspective, what is the boundary condition? First of all, what you need to identify is your equation is second order in space in temperature. Once you do the normal mode assumption, you see it's a second order in space in only one direction in temperature. So, you need boundary conditions for temperature at 0 comma 1, and we are going to take the isothermal case. So, we have isothermal plates, and as the name suggests, when you take isothermal plates, basically you are maintaining the temperature of the plates at TH and TC. So, if you are maintaining the temperature constant, what happens to the perturbations? 0, right? It is the same thing as no slip. If you are maintaining 0 velocity, then perturbations are 0 there. Okay. So, for isothermal case, T hat equals 0 for y equal to 0 comma 1. What is the other extreme of isothermal case? Or let us say insulated condition. Okay, constant heat flux maintains a gradient, insulated is gradient equals 0, right. So, the other condition is that dt hat dy is 0 at y equal to 0 comma 1, okay, which is the insulated condition that you can think about. So, by this you have a closed system, and computationally you can solve this system of equations, okay, because there is no I omega p hat, no. Yes, and you replace that variable in terms of t hat using this equation. Using this, you can think of this equation as a constraint, because this equation has been derived using this. So, this is, I mean, if you guys had done a good course in CFD, then you would know that in incompressible flows, the continuity equation is a constraint. Okay, the continuity equation is a constraint. For compressible flows, actually things are way simpler, because you have an evolution equation for every variable. You have u, v, p, w and t, and you have evolution equation for all variables. Okay, and then you have coupling between all of these, all three thermodynamics into thermodynamic variables using equation of state. But for incompressible flows, the only role of pressure, as you can see from your, if you have done a CFD course and implemented a Navier-Stokes solver, the only role of pressure is to maintain continuity equation. It's a constraint. You can actually formulate pressure in terms of a Lagrangian constraint Lagrangian problem, where pressure turns out to be that Lagrange parameter that you use to minimize something under a constraint, and the constraint is your continuity equation. Where is it? This one. So, pressure is basically a value that is determined by that constraint. So, if you think about it, in this system, since you asked the question, in this system, I haven't included anything about continuity, but that is there. Where does continuity play a role in eliminating pressure using this? Okay. So, once you have this for pressure, now what we either you can do this, or you can follow this procedure where you take the Laplacian of this equation, okay, or you can think about Laplacian as multiplying this equation by again d2 by dy square minus kx square plus ky square. Not multiplying, it is an operator, since this is differentiation, kx square plus kz square. So, I am basically taking this of the y momentum equation. So, I will get minus I omega, let us write this d2 by dy square minus kx square plus kz square as something simpler, and we will write it as d square minus, so what do I give this? I do not want to give too many k, okay, small k square, okay. So, this is not thermal conduction, please, okay. I am just renaming variables here, please be careful. So, we have minus I omega d2 minus k square v hat equals minus d by dy of, or rather d of d2 minus k square p hat plus Ra Pr d2 minus k square t hat plus Pr into d2 minus k square whole square v hat. This is the equation that you will get when you multiply here. And now you can see how we can substitute d2 minus k square p hat from here. You make this substitution and you will get minus I omega So that is RA into PR into dt hat again plus RA into PR to d2 minus k square t hat plus PR into d2 minus k square v hat. And from here you get minus I omega d2 minus k square v hat. So here you will have a minus of RA PR d2 t hat. Here you will have a plus of RA PR d2 t hat. So these terms cancel and you are left with minus k square t hat times RA into PR plus PR into d2 minus k square whole square v hat. There is one more step that we have to do, and that is we have to use the temperature equation. So from temperature equation we know that d2 minus k square t hat equals minus I omega t hat minus v hat. Okay. So what I can do is, so here I have d2 minus k square, here I have k square t hat. I can again take a d2 minus k square of this, and I will have minus I omega d2 minus k square of k square whole square of v hat equals minus k square RA PR. This should have reduced only. Oh, yeah, okay. Okay. So this is where I can leave actually this term because it won't simplify further. You will still have a temperature term in it. Okay. And this is the maximum reduction that we can do for this system. Okay. Now, if you look at Kundu's textbook, so if you look at Kundu's textbook, basically chapter 12 and section 3, you will see by the similar trick that we used for our Orr-Sommerfeld equation. What we do is you multiply this equation with a v hat star and you integrate. Okay, you integrate from 0 to 1. You multiply this equation with a t hat star and you integrate from 0 to 1. By same technique, you can show that omega is always purely imaginary here. As a result of omega being purely imaginary, you have cases where I omega could have a plus sign and a minus sign. I omega could have a plus sign and a minus sign, and for cases where I omega will have a minus sign, if you look here, if I omega has a minus sign, it's a real number, omega is purely imaginary, I omega has a minus sign, then you have your modes growing in time exponentially. Okay, you have your modes that are growing in time exponentially. So in that case, we say that the system is unstable. So omega is always purely imaginary. Okay, you can solve for what is known as the critical state. So the critical state is basically a critical condition is when your omega equals 0, or technically your I omega is 0. Basically, you are trying to solve for that boundary. You are trying to solve for that boundary where I omega crosses from negative to positive or positive to negative and the system becomes unstable. So let us look at that, the critical state when I omega is 0. This is also called the neutral state. Okay. So what is the intuitive let's say intuitive evolution of a neutral state? In a purely stable state, you give some perturbations to the system, perturbations will die down exponentially and you will retrieve back your base flow. A neutral state is where you give some perturbations to the system and they remain as it is forever. So this goes very counter in this is very counterintuitive because the system has viscosity. Okay, the system has viscosity, so you will expect, okay, how can there be any form of perturbation where I disturb the system, I give some waves to the system and they don't die down, they maintain their energy, and that is the beauty of this neutrally stable state. Okay. It is the viscosity and basically conduction and viscosity and their interplay that is causing instability. Okay. And the idea is neutral state is like a situation where both thermal conduction and viscous diffusion are balancing each other just enough so that the system maintains a stable state, okay, but a constant energy state. So this is very important to understand about neutral state, that even though you have thermal dissipation and viscous dissipation in the system, the perturbations don't die down exponentially. So in that, when I omega is 0, the momentum equation basically becomes Prandtl number into d2 minus k square whole square v hat equals Ra into Prandtl number into k square t hat, and the temperature equation becomes d2 minus k square t hat equals minus v hat. Okay. Now let us take a d2 minus k square of this. What do we get? Prandtl number into d2 minus k square whole cube v hat equals Ra Pr k square into d2 minus k square t hat of d2 minus k square of t hat, which becomes minus of v hat. Prandtl number cancels out and then you are left with the system. You have to see this. I can do the derivation, but then you will be like, then I'll be cutting the attendance further in half. It's two board sizes of algebra, but the essence is just doing this only, that you multiply it with v hat star, integrate, multiply with t hat star, integrate. The reason why we are doing this and the reason why it shows or you can get some characteristic values of omega is, as we move to turbulence, this is very much like getting an energy equation. Okay, if you remember, how did we derive the kinetic energy equation? We multiplied, we took the dot product of velocity equation with itself, with velocity. That's how we obtained the kinetic energy equation. There is a general notion of perturbation energy in stability dynamics and linearized dynamics, and the notion is that, let's say you have linearized perturbation equation of any system. So going back to our ODE, let's say you have linearized your system to this, where A is a matrix which is constant in time. Okay. What you can do is you can multiply the system with y prime. Let's say you take a so since these are tuples, I'll make a transpose here, and you can write this as d by dt of y transpose y by 2, because you can add the transpose of this equation and get this, and you will have something like this. No, sorry. Uh, no, you post multiply. So you will have something like this. Now this equation is called the perturbation energy equation. There will be a half. This equation is called a perturbation energy equation. And the idea is, sure, there is a concept of, there is a physical concept of energy. There is a physical concept of energy from thermodynamics you are getting, but this is more like an equation which has a mathematical concept of energy, where let's say you have any dynamical degrees of freedom of the system, you're trying to see what is the energy in that system, okay, without giving any physical meaning to that. Okay, basically if you let's say decouple the physical meaning of energy, what remains? What is energy communicating to you? Let's say a system that has some perturbations, any system, forget about it being any physical system that you have seen, it has some perturbations. What is the energy in that system communicating to you? Why momentum? Let's say the system that you have has absolutely no clue what is velocity or something like that. Okay, this y could as well be, let's say, population of some type of microorganisms. Then what is momentum? Nothing, right? Energy in that case communicates to you what is the amplitude of perturbations. Okay, what it's communicating to you is how high or low you are deviating from the base state. The perturbed state is deviating from the base state. The energy, the mathematical concept of energy is communicating to you how much perturbations you have. Because if you think about, if I give you this vector, perturbation vector, then you can't really say much because that's not a number. But if I give you this number y prime transpose y prime, which is a scalar, then you have at least a number of perturbation. For example, let's say you look at pendulum system. Okay, when you linearize it like that, dy prime by dt, you will have 2 degrees of freedom. One will be angle, one will be angular rotation. Okay, now y prime could be 0 comma 1 and 1 comma 0 as well. Which one has higher energy, or do both of them have same energy? To communicate, to get an answer to that, you will have to consider this instead of just the y prime. It's like considering norm of y prime. So what you are looking at, okay, this is my dynamical equation. What is the rate of change of my norm of perturbations? And sometimes this is also called a perturbation energy norm. Okay, so you can think about this as an equation for perturbation energy norm. Now, given that we have had this nice discussion, you should also expect some question regarding this in your quizzes or exams, where I can ask you to derive a perturbation energy equation after linearizing. Okay, and what you will technically do here is you will multiply these with this and simplify, or try to simplify. So that's how you can get to the conclusion that omega is always purely imaginary. In the textbook, they have written this I omega as some s, and they have shown that s is purely real. Okay, so you can extrapolate from there. So moving back to our equation, just let me make sure I did not make any mistake. Just a second. Just a second. I'll get to you. So we have equals we had, and then we have this by PR minus of. Okay, this seems okay to me. And then I, yeah, this is fine. So d square minus k square whole cube v hat equals minus of Rayleigh number k square v hat. And now this again you can look at it as a differential eigenvalue problem, where the solution will give you the solution. So for a given wave number, or k, for a given wave number to the perturbations, you can determine the critical RA. the critical Rayleigh number where your I omega is 0. Okay, and you can determine the state of the system above this critical Rayleigh number, below this critical Rayleigh number, and you will see that okay, if I increase the Rayleigh number, then I am moving towards instability. If I am decreasing Rayleigh number, I am moving away from instability. Okay, and that really is captured in the definition of your Rayleigh number. Okay, that's captured in the definition of the Rayleigh number. And how is this captured? So let us try to look at physically what does this Rayleigh number, what is this Rayleigh number trying to communicate to us. Okay, so let us look at it from this point of view. So you have alpha delta t h over, let's say, nu, alpha delta t h into g over nu, and then you have an h square by k. Okay, h square by k is what? Kappa, not k. H square by kappa is what? Of thermal diffusion, right? This is your thermal diffusion time scale. Let's call this as tau d. How can I look at this scale? What is this scale trying to communicate? What is this scale trying to communicate? Hmm? So let's say I write this alpha delta t g over nu h as alpha delta t g over h and then an h square by nu. What is this communicating me? Hmm? So h square by nu is viscous time scale, let us say. What is this? Alpha delta t g by h. What is alpha delta t g by h? What are the dimensions of alpha delta t? Alpha delta t. This alpha is not thermal conduction coefficient, conductivity. This alpha was thermal expansion coefficient. Alpha we defined as rho minus rho naught by rho naught equals alpha minus alpha delta t. So alpha delta t is unitless. Alpha delta t times g is the buoyancy force per unit volume. Alpha delta t times g, actually it's the buoyancy force per unit mass, not even volume. So that's acceleration of a fluid particle which has a temperature difference delta t from its surroundings, and how will it start moving up, and that acceleration divided by h is giving you the velocity scale. Okay, that is giving you the velocity scale. Okay, so g by h, g is what? Meter square per second, right? You are dividing it by h. Let's just, I hope I haven't made a mistake in defining this, because this doesn't turn out to be dimensionless, right?
Working with the equation on the right only, right?
Hmm?
The equation that is right on the right side.
Which one?
We are working with those only.
No. I'm trying to give a physical explanation. So I ended up here on of those things. I said that okay, you can get a critical value of Rayleigh number. I'm trying to give a physical intuition of what that Rayleigh number is. Okay.
So as the I omega t cap term.
So we are trying to get the critical state when I omega is 0. Okay. So the physical explanation of Rayleigh number, let's try to focus on that. So we have alpha delta t, this is okay, this is meter square. Oh, this is meters per second square. Okay. I was wrong. So this alpha delta t g by h. So this is your acceleration due to buoyancy. You are dividing it by h. Okay, so that's not going to help because this is meters per second square, and you're dividing it with meters. You're not multiplying it with time. So you can look at it that alpha delta T g times h square by nu is your velocity time scale. Yeah, it's your velocity time scale. Basically, this is your acceleration. Okay, alpha delta t times g is your acceleration, and alpha delta t times g times h square by nu is approximately the velocity of a fluid parcel after time tau nu. Acceleration times acceleration into time gives you the velocity gained in that time, right. So alpha delta t g times h square by nu is the velocity gained. Let us say you have a fluid parcel and this has a temperature. So let's say this is T ambient, this is T ambient plus delta T. So in gravity you are saying, okay, what is the velocity that this fluid parcel gains in time in the viscous diffusive time scale tau nu, and that is this velocity. Okay, and then you have the multiplication. So we had the multiplication with h square by nu, right. So you can really look at Rayleigh number as alpha delta t times g times an h square by nu and times a h by kappa, or h square by kappa 1 by h. Okay, so this is the velocity gained by fluid parcel, and then if you look at this, so kappa h over h square or kappa over h, this is meters per second. This is the rate of diffusion of temperature. Okay. So Rayleigh number, you can really look at it like velocity gained by this fluid parcel, let us say Vp, okay, divided by this rate of diffusion, let us call Vd. Okay. And the physical intuition behind instability is that if your Rayleigh number is very high, if your Rayleigh number is very high, then the rate of diffusion is very small, right. If your Rayleigh number is very high, then rate of diffusion is very small. So that means within this time diffusive time scale, the velocity of the fluid parcel is very large compared to the rate of diffusion. What it's trying to say is that as the fluid parcel moves, so think about it, the problem has both viscosity and thermal conduction. What will thermal conduction try to do? It will try to nullify that temperature difference between the fluid parcel and ambient fluid. What will viscosity try to do? It will try to pull the fluid parcel back, or it will try to accelerate the ambient fluid above. Okay, that's basically the intuition of diffusion. So what that Rayleigh number uh, written like that is trying to communicate to you is that you have a fluid parcel that is moving with some velocity, which has gained some velocity Vp. If the diffusion of temperature difference is negligible in the time it has gained some velocity, then you can think about that the fluid parcel is going to keep moving upwards. It's going to keep moving upwards and upwards and upwards because the temperature diffusion that is happening is very small. Okay, temperature diffusion that is happening is very small. Another important point here is that basically what happens is, if you recall, then your temperature gradient was like this. The temperature is decreasing as you move up. Okay. So, sure, this tells you that increasing Rayleigh number should increase the velocity of fluid parcel compared to thermal diffusive time scale. Now, where is the positive feedback loop of instability? The positive feedback loop of instability is, let us say you have a fluid parcel here, it has some temperature and you move it up. Okay, let us say the fluid parcel has just a bare minimum temperature difference due to which it moved up. Now the temperature of the ambient fluid is even lesser now. Temperature of the ambient fluid is even lesser now. So the just by the act of buoyancy, it has moved in a zone where there is more buoyancy. So it will move further up. Then it will further move up in a zone where there is even more buoyancy. It will keep moving up. and that is the physical intuition behind why there is an instability, because there is a positive feedback loop. You have some perturbation. The nature of the state is that the fluid around that perturbation tries to amplify it. Okay, that's why there is an instability. That just because of small temperature differences, a fluid parcel moves up. Okay, now there are larger temperature differences, moves up further. Even further temperature differences, moves away further. That's your Rayleigh-Taylor instability. Okay, so tomorrow we'll close this and try to look at